So next we are going to solve the differential equation. So recall that our Schrödinger equation has this form. So since we are looking at a bounded system, we expect that psi will go to 0 as the modulus of x goes to infinity. Otherwise, our wave function will not be normalized. So let us first try to solve this equation asymptotically, which means that let's try to solve this equation as x goes to infinity. So in that limit, we see that in the second term that x squared will dominate, so we can ignore the lambda term. So asymptotically, we can expect this equation to become like something x double prime will be given by x squared psi. Now it's easy to verify that psi is equal to some constant times x to the power n, where n is some integer, and e to the power plus minus half of x squared, that this is an asymptotic solution to this asymptotic equation. Now, of course, we're taking both plus sign and minus sign here. Recall that for the plus sign, this will no longer be a bounded or normalizable wave function, because as x gets large, this wave function will become larger and larger. The plus sign doesn't really make sense, but we're going to take the plus sign because we are going to see that it's going to rear its ugly head in some other form. So let's just take it for the time being. So if I now take the first derivative of psi, so psi prime is going to be c times n x to the power n minus 1. So we are taking the derivative of this guy, and then we have e to the power plus minus half of x squared, and then we have c x to the power n, and then we are going to have plus minus x from taking derivative of the exponential, and then we have the exponential. And of course, this is just going to be cn x to the power n minus 1, and then we are going to have plus minus c x to the power n plus 1, and then the whole thing multiplied by the exponential part. And now if I take the second derivative, so the second derivative, we're going to have quite a few terms. So from the first term, we're going to have c n times n minus 1 x to the power n minus 2. And then we are going to have take the derivative of the exponential factor. So we are going to have plus minus coming down, then we have c, and there was already a factor of n before, and then from the x there was x to the power n minus 1, but we're going to get a factor of x, so this is going to become n, and then we're going to take the derivative of this second term. So if I do that, then the first term we're going to have plus minus c n plus 1 times x to the power n, and then taking the derivative of this thing, we are going to get so it's going to bring down plus minus, so that's going to multiply plus minus to give me just plus. So I'll just have plus, and then I have c, and then there would be a factor of x coming down, so we have x to the power n plus 2. And the whole thing is going to be multiplied by e to the power plus minus half x squared. So what is our differential equation going to be? Our differential equation is going to be that, so if I take the limit where x goes to infinity, okay, before we do that, let's just, simplify this a little bit. This will be c, so, there are two terms here, like this term and this term, they're going to add up. So they're going to add up to give you 2n plus 1. So now if I factor out c times x to the power n plus 2, and of course we have the overall factor of e to the power plus minus half of x squared. Then inside the bracket we'll have 1, so this is coming from this term. And then we'll have, these two guys, and that would be plus minus, say 2n plus 1 divided by x squared, and then this term, which will be n times n minus 1 divided by x to the power 4. Now in the limit where x goes to infinity, we see that these two terms will drop out, and what we'll have left is c x to the power 2. Let's just take the c inside the bracket, and we'll have c, we'll have x squared e to the power plus minus half of x squared. So this is going to be x squared psi. So we see that precisely that this differential equation is satisfied by this solution. So this is the asymptotic solution. So we see that this thing has the form of some x to the power n times e to the power plus minus half of x squared. So of course we want to take the minus sign here because we want it to be normalizable. So for the exact solution, we take the ansatz that this will be some function phi of x e to the power minus half x squared, where we are requiring that as x becomes large, this phi of x becomes this factor. Now let's see if we can manage to find a solution like that. What we now do is that we insert this exact ansatz into our exact wave or exact equation, which is this equation, right? So let me just rewrite this here just to remind ourselves. Our exact Schrödinger's equation is this thing, sorry. And when we insert our ansatz into this equation, what do we get? We get, after a little bit of algebra, which I'll leave as an exercise, we get an equation for phi. So we get an equation where we have the second derivative of phi minus 2x, first derivative of phi, plus lambda minus 1, phi equals to 0. So how do we solve this differential equation? So this differential equation, let us take the ansatz of a series ansatz. So let's, this is our proposed solution. So of course we don't want it to blow up. That's why we are taking this to be a sum over a positive power series, a power series with positive exponents. Otherwise it would blow up. So if we do this, then using the series method, if I take the first derivative of phi, we get And if I take the second derivative of phi, okay, so now what we're going to do is that we are going to insert this into our differential equation, and then we get n goes from 0 to infinity. The first term was phi double prime, so we get n times n minus 1 a n x n minus 2, and then we get, for the second term, what do we get? We get something multiplied, the phi prime multiplied by minus 2x. So we get minus here and 2, and there was n, a n, and now x to the power n because of this extra factor of x. And for the last term, we get plus lambda minus 1 a n x to the power n. And this is 0. So of course the values of x are arbitrary, and therefore for this equation to be valid, all the coefficients of each power of x must be 0 identically. Okay, before we use that impose that condition, let's just rewrite this in slightly more tidy form. So what is the lowest exponent in this equation of x? So when n is 0, we see that the exponent of x is going to be 1 over x squared. So we start with 1 over x squared. And what is its coefficient? Its coefficient is, the second term is not going to contribute because a to the power minus 2n is not something, is 0, because our series ansatz just starts at n equals to 0. So a with the subscript n less than 0 is 0. So this term is not going to contribute anything. It's going to contribute this. So if I put n equals to 0 here, we see that we get 0 times minus 1 times a0 is equal to 0. So this doesn't really fix a0. Okay, the second term, next term will be the coefficient of x to the power minus 1. Again, the second term in this equation is not going to be contributing. So from the first term, we get 1 times 0 times a1 equals to 0. Again, this does not fix a1. So if we now go to the next thing, which is say x0, next term, so we get say 2, because x is 0 means that x to the power 0 here means that n has to be 2 in this term. So we get n equals to 2 and n equals to 1 from here. 2 times 1, and then we have a2. And then over here, we are going to get, here in the second term, n is 0, so we get 2 times 0 minus lambda minus 1 times a0. So thus we see that we get a recursion relationship where if I had fixed a0, that would fix a2. So we can actually find the general recursion relationship very easily, and it turns out that the coefficient of x to the power n will be given by n plus 2 times n plus 1 times a n plus 2, and that will be given by 2n plus lambda minus 1 times a n. So we can rewrite this recursion relationship as n plus 2 is equal to 2n minus lambda minus 1 n plus 2 n plus 1 times a n. So this is the recursion relationship which solves our differential equation. So we get two solutions for two choices of A0 and A1. So remember, they're not fixed. So if we choose, say, A0 to be, okay, let's choose A1 to be 0, then that means that all the odd coefficients like A3, A5, A7, all of them are 0. So in that case, our solution becomes, let's call that phi 0 of x. That becomes A0 plus A2 x squared plus A4 x4 plus dot dot dot. In other words, it's an even function. So on the other hand, if we had chosen A0 to be 0, then that would mean that A2, A4, A6, all those even A's are 0. In that case, the solution is given by A1x, A3x cubed plus A5x5. In other words, an odd function. So these are the two classes of solution to our differential equations. And of course, it's easy to see that they're linearly independent. That phi 0 of x and phi 1 of x are linearly independent because one is an even function, the other one is an odd function.